Hello everyone, and welcome. I'm so glad you could join me today. We're about to dive into a really critical topic in the world of industrial cybersecurity, lateral movement within our operational technology, or OT, networks. Specifically, we'll be looking at what we call deep lateral movement. This is something that's becoming a more and more common tactic for attackers trying to get at our industrial control systems. And it's one of the most sophisticated ways they try to do it. Over the next hour or so, we're going to explore this together. We'll break down how these attackers manage to move, almost unseen, between different parts of our control networks, especially at the controller level. That's Purdue Level 1. For those familiar with the model, we'll talk about what this means in the real world, the kind of impact it can have, and most importantly, we're going to arm ourselves with practical ways to defend our critical infrastructure against these threats. This isn't just going to be theory either. We'll look at actual incidents, real case studies, and see exactly how these ideas play out in the field. It's all about making these concepts tangible and actionable for you. So, let's start with a really fundamental question. What exactly is deep lateral movement in OT networks? When we talk about lateral movement in our typical IT environments, the corporate networks, the business systems, we usually mean an attacker who's gotten a foot in the door, maybe compromised one computer, and is now trying to move sideways to other systems, looking for more valuable targets or more access. It's a well understood concept there, but in OT environments, and especially when we get down to what's called Purdue Level 1, the level where our controllers like PLCs and RTUs operate, lateral movement takes on a whole new dimension of seriousness. Why? Because these are the devices that are directly interacting with the physical world. They're opening valves, spinning turbines, managing safety systems. So, an attacker moving around at this level can cause direct physical consequences. Deep lateral movement then refers to something very specific. It's an attacker's ability to cross the security boundaries that we've set up at that controller level at level 1. They're moving through our controller networks to reach devices that, by design, should be segmented or isolated. These devices shouldn't be directly accessible from other parts of the network, or certainly not from outside. This kind of movement could let them sneak into our safety systems, for example, or get to specialized field devices, or equipment that's supposed to be tucked away behind layers of protection. They're finding ways to bypass the very safeguards we've painstakingly put in place. Now, you might be thinking, okay, that sounds bad, but why is this such a big deal for me? Why should I care so much about this specific type of attack? Well, here's the thing. For years, a lot of OT security has really and rightly focused on protecting the perimeter, that boundary between the IT network and the OT network, that IT-OT convergence point. We build strong walls there. But sophisticated attackers know this. They know we're watching the main gate, so to speak. So, they look for other ways in, or other ways to move, once they're in. Deep lateral movement often exploits those lower-level interconnections, the ones within the OT network, that maybe haven't received the same level of scrutiny. Understanding these hidden pathways, these less obvious vectors, is absolutely essential if we want to build a truly comprehensive defense for our critical systems. It's about seeing the full picture, not just the most obvious entry points. To really get a grasp on this, let's just take a quick moment to refresh our understanding of the context we're working in. Most OT environments, as many of you know, are structured using something called the Purdue Enterprise Reference Architecture. It's a model that organizes our industrial systems into different functional levels. At the very bottom, level 0, we have our sensors and actuators. These are the devices actually touching the physical world, measuring temperature, opening a valve, starting a motor. Then, just above that, at level 1, we have the controllers. These are the brains of the operation at a local level. Things like programmable logic controllers, PLCs, and remote terminal units, RTUs. They take information from level 0 sensors and send commands back to level 0 actuators. Level 2 is where we find our SCADA, supervisory control and data acquisition systems, and our HMI, human-machine interface systems. This is where operators monitor the process, make adjustments, and see what's happening. And then levels 3 and up move progressively towards the business systems, manufacturing execution systems, enterprise resource planning, and so on. Our main focus today, the heart of our discussion, is right there at level 1, that controller level. Because these are the systems that are directly in charge of controlling physical processes. If an attacker compromises these, the impact can be immediate and can have very real-world consequences: equipment damage, production outages, or even safety incidents. Think about that for a moment. The direct link between a compromised controller and a physical event. It's a sobering thought, isn't it? Now, when attackers set their sights on performing this kind of deep lateral movement at level 1, they usually have one of two primary motivations, or sometimes both. The first big motivation is what we call perimeter crossing. Imagine an attacker wants to move from one network segment with a certain security profile to another network segment that's supposed to be much more secure. For example, moving from a basic process control system, our BPCS, into a safety instrumented system, our SIS. These systems are often kept separate for very, very good reasons. The safety system is our last line of defense. It's there to prevent dangerous conditions, to shut things down safely if the main control system goes haywire, or if something unexpected happens in the process. If an attacker can cross that perimeter, they can potentially disable or manipulate those critical safety functions. And the consequences of that? They could be catastrophic. The second main motivation for attackers is to gain granular control. They want to get incredibly detailed access. The kind of access they need to manipulate very specific devices or to bypass particular safety constraints that are built into the system at a low level. They aren't just trying to flip a switch from on to off. They're trying to change how the switch works or what happens when it's flipped. Let's talk a bit more about that first motivation, perimeter crossing, especially between the BPCS and the SIS. Industry standards and a lot of expert guidance have led to a few common ways these systems are architected in relation to each other. You might see a completely separated architecture. This is where the BPCS and SIS are fully air-gapped. No direct connection at all. That's ideal from a security perspective for that boundary, but not always practical for operations. Then there's the integrated architecture. Here, communications between the BPCS and SIS might happen, but they go through some form of firewall-based segmentation. There's a controlled pathway. And then we have the interfaced architecture, which is particularly interesting for our discussion today. In this setup, there's a restricted link, often a point-to-point serial connection, or a very specific Ethernet link that carries a limited amount of information between a BPCS controller and an SIS controller. Maybe the SIS needs to know a certain process variable from the BPCS to make its safety decisions, or the BPCS needs to know the status of the SIS. Another technique attackers can use is direct memory manipulation. Controllers like PLCs typically have memory maps that are divided into different areas. There are areas for the I/O image tables, which reflect the state of the inputs and hold the commands for the outputs, areas for timers and counters, internal data registers, and of course, the area that holds the actual control logic program. Now, parts of this memory, particularly data areas, may be exposed for reading or writing through various industrial protocols. This is often necessary for HMIs to display data or for other systems to interact with the PLC. While the sensitive areas that hold the actual program code are usually protected against direct writes during normal operation, you often need special engineering software or to put the PLC in a specific mode to change the code. Attackers might still be able to modify other data areas that can indirectly influence the flow of that code. For example, they might be able to overwrite values in data registers that are used in calculations or decision-making by the program. Or, in more advanced scenarios, they might target things like function pointers or dispatch tables stored in memory. If they can change where the code looks for its next instruction or which piece of code to execute based on a certain condition, they can effectively redirect the execution path without directly changing the stored program code itself. Think of it like this. Instead of rebuilding all the roads in a city, which would be like rewriting the entire PLC program, an attacker just changes a few crucial signposts. By modifying where those signposts point, they can make traffic, the program execution, go down a completely different and potentially malicious path. This is a much more subtle way to alter the system's behavior and can be harder to detect than a wholesale program change. Finally, we have to consider protocol stack vulnerabilities. This is a persistent and widespread threat. The firmware in our embedded controllers and field devices is often written in memory-unsafe programming languages like C and C++. These languages give programmers a lot of power and control, which is great for performance in resource-constrained embedded systems. But they also place a lot of responsibility on the programmer to manage memory correctly. If they make mistakes, it can lead to vulnerabilities like buffer overflows, use after free errors, or other memory corruption issues. Attackers can then try to exploit these vulnerabilities by sending specially crafted messages over the network to the device. If the device's protocol stack, the software that handles interpreting the network messages, has such a flaw, the crafted message could cause it to crash, or worse, allow the attacker to execute arbitrary code on the device. And contrary to what some people might believe, these kinds of vulnerabilities are not just limited to IP-based protocols like TCP/IP or UDP/IP, non-IP-based serial protocols, proprietary field buses. They are just as susceptible to these memory corruption vulnerabilities in their parsing and handling routines if they are not programmed carefully. It's a fundamental challenge in embedded systems development. So, we've talked about the motivations, and we've talked about the common tactics, techniques, and procedures. Now, how might all of this play out in a realistic scenario? Let's consider an attack against a piece of movable bridge infrastructure. Specifically, let's think about a bascule bridge. That's the kind of bridge where one or two sections or leaves pivot upwards to allow boats to pass underneath. When the bridge leaf is open, it's typically held in place by a counterweight system and various locking mechanisms. In this hypothetical scenario, let's say an attacker wants to cause significant physical damage to this bridge. A typical safe bridge closing sequence involves multiple, carefully orchestrated steps. The powerful motor systems will drive the bridge leaf downwards. As it approaches the fully closed position, limit switches will trigger, signaling the control system to decelerate the leaf to a much slower creep speed for the final part of the closure. This is a critical safety measure to ensure it seats properly and doesn't slam into the abutment. Once it's fully closed and seated, the main drive system stops, and then heavy lock bars, sometimes called span locks, will engage to physically secure the leaf in place, making it safe for traffic to cross. Now, an attacker with deep access to the control system might try to do several malicious things that the normal SCADA interface would never allow. They might try to open the bridge leaf while the lock bars are still engaged. This would put immense stress on the lock bar mechanisms and the drive motors, likely bending or breaking them and potentially jamming the bridge. Or they could attempt to close the bridge at full speed without decelerating to creep speed. Imagine the force of that massive bridge leaf slamming down. This could severely damage the bearings, the alignment of the leaf, and the lock bar mechanisms when they try to engage. Another damaging action could be to trigger an emergency stop command while the bridge leaf is moving at its maximum velocity. The sudden immense inertial stress on the motors, gearboxes, and the entire bridge structure could be devastating. None of these destructive actions would typically be possible through the normal SCADA interface or HMI screens that the bridge operators use. Why not? Because the bridge control system, by its very design, is filled with safety interlocks and operational constraints specifically to prevent such dangerous operations. These safeguards are there to protect the equipment and ensure public safety. So, to achieve these kinds of damaging impacts, an attacker would need to go deeper. They would need to perform that deep lateral movement we've been discussing. They might start from a compromised central management system, perhaps in a corporate or municipal network. Then they'd have to find a way to cross into the OT network controlling the bridge. From there, they'd need to potentially bypass or compromise the field bus coupler that serves as the interface between the central SCADA system and the bridge's local control system. Once past that, they would likely need to compromise the main PLC or controller for the bridge to gain access to the field bus network that connects to all the field devices, the motors, the limit switches, the sensors for the lock bars. And if the system also incorporates separate safety controllers, an SIS for the bridge, if you will, the attacker would also need to find a way to bridge that gap, to compromise or disable those safety functions as well, to allow these dangerous actions to proceed. This isn't just a far-fetched, theoretical exercise. In 2023, there was a real-world incident on the Brickell Avenue Bridge in Miami. It involved significant damage to the lock bar mechanisms, reportedly due to issues with limit switch failures, leading to the bridge trying to operate against a still engaged lock. Now, that particular incident wasn't attributed to a cyber attack, as far as we know, but it perfectly illustrates the kind of physical impacts that could result from the type of deliberate, malicious control system manipulation we're talking about. The vulnerabilities and potential for damage are very real, but enough theory and hypothetical scenarios for a moment. Let's look at a concrete, real-world example of an attack that explicitly crossed these critical safety perimeters. One of the most notorious cases, and one that really sent shockwaves through the industrial control system community, is the Triton malware, which was discovered back in 2017. This was an incredibly sophisticated attack, and it specifically targeted Schneider Electric Triconnect's safety instrumented systems. The target was a petrochemical facility in the Middle East. What made Triton so particularly concerning, so alarming, was its explicit focus on compromising the safety systems. This wasn't about stealing data or causing a denial of service on the business network. This was about getting into the last line of defense against a major industrial accident. The attackers, in that case, followed a complex path. They first gained initial access to the plant's IT networks, the corporate side. From there, they managed to pivot into the OT networks, the process control environment, and eventually, after careful reconnaissance and movement, they reached the engineering workstation that was specifically used to program and configure the Triconnect safety controllers. This is a critical asset, holding the keys to the safety kingdom, so to speak. From that compromised engineering workstation, they deployed their custom malware, Triton, which was specifically designed to interact with the firmware of those safety controllers. The Triton malware essentially implemented a backdoor into the safety system. This backdoor could have been used by the attackers to prevent the safety systems from performing their intended function during a critical event. Think about that for a second. This could have allowed the attackers to do one of two things. They could have caused the plant to shut down by triggering false alarms or spurious trips in the safety system. This would be disruptive and costly, but perhaps not catastrophic. Or, and this is far more worrying, they could have set things up so that the safety system would not respond to actual dangerous conditions in the plant. If a real emergency occurred, the SIS might fail to act, potentially leading to physical destruction, release of hazardous materials, or even harm to personnel. Fortunately, in the Triton incident, the attack was discovered somewhat accidentally. Some of the targeted safety controllers entered a fail-safe state. They shut down the process they were protecting because of errors in the attacker's own malicious code. It seems their malware wasn't perfectly programmed, and it caused the controllers to trip. But the incident was a stark wake-up call. It clearly demonstrated a sophisticated understanding by the attackers of these deep lateral movement techniques, and it showed their willingness to specifically target that critical boundary between the basic process control system, BPCS, and the safety instrumented system, SIS. It was a game changer in how we think about ICS threats. And this isn't an isolated type of threat that just disappeared after Triton. More recently, in 2022, another malware framework called InController also sometimes referred to by other names like pipe dream, was discovered. This was a highly capable toolset, and it showed a clear capability for routing various industrial protocols between different networks. It was like a Swiss Army knife for ICS attacks. This in-controller framework included components that could communicate with a variety of industrial control systems from different vendors. It had modules for manipulating physical processes directly by interfacing with field devices, often through the controllers themselves. It demonstrated an ability to understand and speak native ICS protocols. And importantly, for our discussion on evasion, it also showed an ability to try and hide its presence from detection by masquerading as legitimate engineering software or normal network traffic. It was designed to blend in, making it harder to spot. This again highlights that attackers are actively developing and using tools that facilitate deep lateral movement within our OT environments. It's clear these threats are real, they are sophisticated, and they are evolving. So, the crucial question for all of us is, how do we defend against them? How do we protect our critical systems from these kinds of deep lateral movement attacks? It's not just about building a bigger wall at the IT-OT boundary anymore. We need to think deeper. Let's explore some of the strategies we can employ, drawing from what we've discussed and from established best practices. And as we go through these, I want you to be thinking about your own environments. Where are your potential weak spots? Where can you strengthen your defenses? This interface architecture is where things can get tricky. That link is supposed to be secure by design, precisely because its capabilities are limited. It's not meant to carry complex data or allow programming access. But, and this is a big but, it can still represent a potential pathway for a sophisticated attacker who knows how to exploit it. Think of it like this. If you're defending a castle, you'd naturally focus your main defenses on the main gate, the drawbridge, and the high stone walls. You'd have guards there, fortifications. But what if there's a small, lesser-known, narrow tunnel running underneath the castle? Maybe it connects the main keep to a nearby watchtower, or an old escape route. If an attacker discovers that tunnel, it becomes a prime target, doesn't it? They can bypass all your strong defenses at the main gate. Well, these level 1 connections between controllers, like that interfaced BPCS-SIS link, can be like that tunnel. They can allow an attacker to bypass your carefully designed network segmentation and defenses if those specific links aren't properly secured and monitored themselves. Have you thought about all those little tunnels in your own environments? Another type of perimeter at level 1 that's often underestimated involves devices called field boost couplers. These devices are designed to connect different types of networks or protocols. They are frequently used to provide limited interfaces to what are sometimes called packaged units. These are specialized control systems that handle a specific function, perhaps for a piece of equipment, and are often supplied and maintained by an external third-party vendor. Let's imagine a municipal water treatment system, for instance. You might have the main control system for the overall plant, but then there's a specialized chemical dosing skid, a packaged unit, that's responsible for adding very specific chemicals in precise amounts. This skid might be provided by a vendor who also remotely maintains it. The main plant control system needs to communicate with this dosing unit, perhaps to tell it the current water flow rate or to get status information. This communication often happens through a field bus coupler, and that coupler is supposed to limit the information exchange to just a few predefined variables. It acts as a gatekeeper, or so we assume. Historically, these field bus couplers were pretty simple devices. They did one job, like protocol conversion, and had a minimal attack surface. They were, for lack of a better term, dumb devices from a processing standpoint. But here's the catch. Modern field bus couplers have become progressively smarter. They now have more complex protocol conversion capabilities. They might have embedded web servers for configuration. They might even support firmware updates that can be pushed over the network, what we call in-band updates. This expanded functionality is great for convenience and features, but it also means a significantly expanded attack surface. I've personally encountered several real-world situations where organizations had designed their security architectures based on the assumption that these field bus couplers were just simple, non-threatening devices. They believed the couplers were dumb and therefore not a significant risk. But on closer inspection, we discovered that these very devices actually presented significant lateral movement opportunities for attackers. It's a classic case of security by assumption rather than security by verification. We assume a device is simple, so we don't look too closely. But the technology has moved on, and so have the attacker's capabilities. It really makes you think, doesn't it? Are there devices in your network that you've assumed are too simple to be a threat? Now, let's shift to that second motivation we talked about: gaining granular control. In many complex industrial architectures, it's quite common for our level 1 control networks to have a sort of hierarchy. You might have master PLCs that are connected to multiple nested device networks. These nested networks could contain slave PLCs, remote I/O modules, variable frequency drives, and other intelligent field devices. The master PLC, which might be the one communicating with the level 2 SCADA system, often only exposes a limited subset of parameters and functions to that higher level. This is good for simplifying operations and can provide a layer of abstraction. But for an attacker who wants to cause very specific or very damaging effects, interacting only with that master PLC and its limited exposed functions might not be enough. They might not be able to achieve their goals. To cause more significant damage, or to manipulate the process in a very precise way, these attackers need to reach those nested devices directly. They need to get past the master PLC and talk to the slave PLCs or the intelligent remote I/Os that are actually controlling the fine details of the process. This often means they would first have to compromise the master PLC itself. And then, once they have control of that master PLC, they can use it as a kind of stepping stone, a pivot point, to access those other devices deeper in the network that aren't directly reachable from the level 2 systems or from other network segments. Consider a large dam control system, for example. The main SCADA system at level 2 might have the ability to send a command to a master controller at level 1, instructing it to open or close the spillway gates. And this operation would normally be governed by a set of predefined safety parameters and interlocks programmed into that master controller. For instance, it might prevent opening the gates too quickly, or opening them if water levels are too low. But what if an attacker wants to cause truly catastrophic consequences? Maybe they want to override the specific speed limits on the individual gate motors to cause them to tear themselves apart. Or perhaps they want to bypass the interlocks that prevent dangerous operations, like trying to open a gate when there's an obstruction. That level of fine-grained, dangerous control usually requires much deeper access than what's available through the main SCADA interface, talking to the master PLC. They need to get into that level 1 network and talk directly to the components controlling those motors and sensing those interlocks. Furthermore, many field devices themselves have internal safety constraints built into them. For example, a variable frequency drive, VFD, that controls a large motor might have built-in limits on how quickly it can accelerate or decelerate the motor to prevent mechanical stress. It might have protections against voltage spikes or overcurrent situations. These protections are often deeply embedded in the device's firmware. And critically, these internal safety parameters can sometimes only be modified through specialized configuration interfaces or engineering tools, not through the normal operational commands the device receives. An attacker who is intent on causing physical damage, perhaps by overspeeding a motor or disabling its protections, would absolutely need to bypass these internal constraints. And that, again, requires the kind of deep, granular access at level 1 that we're discussing. They need to get right down to the device level. Understanding these motivations, crossing perimeters, to access supposedly isolated systems like safety systems and gaining granular control over specific field devices gives us a much clearer insight into how attackers approach these OT environments and why deep lateral movement is so attractive to them. It's not just random exploration, it's targeted. But knowing why they do it is only half the battle. We also need to understand how they do it. What specific tactics, techniques, and procedures, or TTPs, do they actually employ to achieve this deep lateral movement at the controller level? There are several key methods we see being used, and it's important to be aware of them. First up is protocol routing and tunneling. This is a really big one. Many of the industrial protocols we use every day in OT networks are, by their very design, highly routable. This means that messages using these protocols can be made to traverse different nested device networks. They can hop from one network segment to another, often through controllers that are connected to multiple networks. Protocols like CIP, Common Industrial Protocol, Siemens S7Com, EtherCAT, and features like Profinet's Transparent Device Access all have functionalities that can enable this kind of routing. And here's something that might surprise some of you. Did you know that many PLC backplanes, the internal communication bus within a modular PLC rack that connects the CPU to its I/O modules, communication modules, and other special function modules, are themselves often based on these same routable protocols? This design is great for flexibility and makes it easy to expand the PLC's capabilities by just plugging in new modules. But it also means that these backplanes can, in some circumstances, create potential attack paths if an attacker can get a foothold on one module and then try to reach another across that backplane, or even use it to bridge to another network connected to a different module. Beyond just routing the native protocol, there's also the issue of tunneling. Some industrial protocols have features that allow completely different protocols to be encapsulated or tunneled through the main protocol. Think of it like putting a smaller envelope inside a larger one. Examples include things like Modbus, encapsulated interface transport, which can carry Modbus RTU over TCP IP, or HART pass-through, which allows HART configuration messages to travel over 4 to 20 might say current loops or through remote I/O systems, and even certain reserved FL net codes in some Japanese industrial networks that can be used for tunneling. An attacker who understands these capabilities might be able to sneak commands for one type of device through a network that's supposedly only carrying traffic for a different protocol, bypassing simpler firewalls or inspection systems that are only looking at the outer protocol layer. It's a clever way to hide their tracks or reach otherwise inaccessible devices. The next method we often see is in-band code downloads. Our controllers, our PLCs, our RTUs, and even many intelligent field devices typically need to have their logic or their firmware updated from time to time. This is normal to fix bugs, add features, or patch vulnerabilities. The question is, how does this update happen? If this update functionality, the downloading of new code or firmware, occurs over the same communication link that the device uses for its regular operational data, what we call an in-band update. And if this update can happen without needing someone to physically interact with the device, like flipping a switch or pushing a button, what we call a hot update or an online change, then this represents a potential attack vector. Consider that field bus coupler we talked about earlier, the one connecting two different networks, maybe a process control network and a vendor-maintained packaged unit network. If that coupler supports hot firmware updates that can be initiated remotely over the network, an attacker who manages to gain access to one side of that coupler could potentially try to rewrite its firmware. And if they can rewrite the firmware, they could change its behavior to breach the very perimeter it's supposed to be maintaining. They could turn that gatekeeper into an open door. Not all devices have this capability for hot in-band updates, of course. So, understanding the exact make, model, and firmware version of your devices is absolutely crucial for assessing this particular risk. You need to know what your devices are capable of, not just what they usually do. Do you have a full inventory and understanding of these capabilities for your critical level 1 devices? It's a vital question to ask. Whew! That was a lot of ground to cover on specific defenses related to deep lateral movement. But this is just one facet of the broader challenge of lateral movement in all ICS environments. Let's broaden our perspective a little and think about how these ideas connect to a wider range of attacker techniques and how we can build a more holistic defense. Imagine an attacker has gained that initial foothold, maybe through a phishing email that an engineer clicked on, or perhaps they exploited a vulnerability on an internet-facing server that had an overlooked connection to the OT network. Their first objective is usually not their ultimate one. Once they're in, their next big goal is often to move laterally, to explore the network, to find more critical systems, to escalate their privileges, get more power, and ultimately to achieve whatever their malicious goal is. This could be anything from quietly stealing sensitive process information, espionage, to actively disrupting operations, or even causing physical damage. Understanding the ways they try to move laterally once they are inside any part of your IT or OT landscape is absolutely crucial if we want to develop truly effective defense strategies. Now, in the cybersecurity world, we often try to categorize and understand attacker behavior using frameworks. One very useful one is the MITRE ATNCK-R for ICS framework. It's like a big knowledge base that describes the different tactics and techniques that adversaries have been observed using in real-world attacks against industrial control systems. It gives us a common language, a common way to think about and talk about these threats. When we talk about lateral movement in this context, it's not just one single technique. Attackers often chain together several different tactics to achieve their aims. They might use techniques related to collection, gathering information, command and control, talking back to their home base, evasion, avoiding detection, execution, running their malicious code, and of course, lateral movement itself, often combined with privilege escalation, getting more rights on a system. Another really important set of guidelines comes from the IEC 62443 series of standards. This is an international framework specifically designed for improving the security and availability of what they call industrial automation and control systems, or IACS, which is basically our OT environments. IEC 62443 looks at security from many different angles: policies and procedures, system-level security requirements, and even security features that should be built into individual components like PLCs or sensors. When we're thinking about countering lateral movement, key concepts from IEC 62443 like proper network, segmentation, robust access control, and continuous security monitoring are incredibly relevant and provide a strong foundation. And then there's another helpful resource from MITRE called D3Fend Say TM. If ATTNCK tells us how the attackers attack, D3Fend is like a knowledge graph of cybersecurity countermeasure techniques. It helps us, as defenders, understand how different defensive technologies and methods can be used to counter those specific offensive techniques described in ATTNCK. It gives us a structured way to map our defensive capabilities directly to the attacker's actions. So, if an attacker is using technique X, D3Fend can help us identify defensive technique Y or Z that could stop them or at least detect them. Now, trying to find, say, 20 completely distinct, publicly super well-documented ICS malware case studies where every single detail of their lateral movement TTPs, tactics, techniques, and procedures is laid out is actually quite challenging. As you can imagine, organizations that suffer these kinds of attacks are often, and understandably, very hesitant to share all the gory details publicly. It's sensitive information, but we do have some very prominent examples, like Stuxnet or Indestroyer Crash Override, and we can also look at common patterns and the capabilities of malware toolkits like InController that we discussed. From these, we can extrapolate and understand the general ways attackers operate and then build our defensive strategies. So, let's try to walk through a few illustrative scenarios. For each one, we'll try to pinpoint the specific way the malware might try to move laterally, using the kind of language MITRE for ICS uses. Briefly describe how that attack might unfold. Then, think about the countermeasures, drawing on the principles from IEC 62443, like segmentation or access control, and the defensive techniques from D3FEND, like network traffic analysis or hardening configurations. But we'll talk about them in plain language, focusing on what we do rather than citing standard numbers. And finally, we'll try to blend these together into a holistic defense strategy for that scenario. Scenario 1. Attackers exploiting remote services like RDP, VNC, or SSH. So, picture this. An attacker is looking for systems that allow remote connections, maybe remote desktop protocol, RDP, on an engineering workstation in the OT network, or VNC to an HMI, or even SSH into a server. This is a very common technique. Malware like NotPetya, while it was primarily an IT-focused nightmare, had a huge impact on ICS environments precisely because these IT and OT networks were interconnected, and it spread by exploiting things like SMB services and trying to use stolen credentials. A hypothetical ICS-specific malware could do something very similar. Scan the OT network for open RDP ports, for example, and then either try to exploit a known vulnerability in that RDP service, or try to use weak or stolen login credentials to simply log in to that engineering workstation remotely. Once they're on that workstation, they have a new launchpad for further attacks within the OT zone. How do we defend against this? First, strong access control is paramount. This means every user account, especially those that can be used for remote access, needs a strong, unique password. And wherever humanly possible, we should be using multi-factor authentication, MFA. If an attacker steals a password but doesn't have that second factor, they still can't get in. We also need to make sure that only specifically authorized systems are even allowed to initiate these remote connections to critical assets. And of course, the principle of least privilege applies. Users and even service accounts should only have the bare minimum access rights they absolutely need to do their job. If an account doesn't need to log in remotely, then it shouldn't be allowed to. Then, we need to think about system integrity and how we manage these remote services. We must ensure that the remote service software itself, the RDP client and server, the VNC software, is kept patched and up to date. These services often have vulnerabilities discovered in them, and attackers are quick to exploit unpatched systems. We should also be protecting the data that flows through these remote sessions, perhaps by ensuring they are encrypted. And critically, network segmentation and restricted data flow are our best friends here. We need to isolate our critical control systems from less secure networks. If you have engineering workstations that need RDP access, maybe they should be in a specific controlled zone, and firewall rules should strictly limit what other systems they can connect to and what can connect to them. We can use demilitarized zones, DMZs, to control access to and from the OT environment from the corporate side. And even within the OT network, we can think about micro-segmentation, creating smaller, isolated segments to limit the blast radius if one host, like that RDP-enabled workstation, gets compromised. The goal is to make it so that even if an attacker gets onto one system via RDP, they can't easily reach everything else. We also need strong boundary protection, firewalls, and other security controls at the edges of these zones. Finally, we need to be watching and ready to respond. This means logging all remote access attempts, both successful ones and failed ones, and not just logging them, but actually monitoring those logs for anomalous behavior. Is someone trying to RDP into a critical server from an unrecognized IP address? Are there an unusual number of failed login attempts followed by a success, which might indicate a brute force password guessing attack? We can use network traffic analysis tools to monitor the RDP, VNC, or SSH traffic itself. Is there suddenly a huge amount of data being transferred over an RDP session that normally only has light traffic, that could be a red flag. Host-based intrusion prevention systems on the workstations and servers can also help by blocking or alerting on known exploits that target these remote services. Some advanced tools can even analyze the context of a remote session, how long it lasts, what commands are being run, the user's typical behavior, to spot anomalies. So, the blended strategy here is robust network segmentation to limit the reach of any compromised remote service, strong authentication and authorization for all remote access, with MFA as a top priority, keeping those remote service applications patched and secure, and then continuous monitoring of network traffic, session activity, and logs to detect any malicious or anomalous use of these services. Every layer helps. Does your current setup for remote access incorporate these kinds of layers? Scenario 2. Attackers transferring tools or malware, using file shares like PSExec or SMB shares. Okay, next scenario. An attacker has compromised an initial host in the OT network. Now they want to spread their tools or their malware to other systems. A very common way they do this is by using legitimate administrative tools or their own custom malware and transferring them across the network using protocols like SMB CIFS. That's the protocol behind Windows file sharing and those admin shares. They might use a tool like SecSec, which is a legitimate Microsoft tool for running processes on remote systems, but attackers absolutely love it for lateral movement because it can look like normal admin activity if you're not watching closely. They often use it in conjunction with compromised credentials they've managed to steal. We saw this with Stuxnet. It used multiple methods to propagate, and one of them was exploiting an SMB vulnerability to spread. What can we do about this kind of lateral tool transfer? Again, strict access control over administrative credentials is key. Who has the rights to use tools like PSExec? Which accounts can connect to administrative shares on other machines? We need to limit these powerful privileges as much as possible. Then, we need to think about system integrity and preventing malicious code from running. This is where application whitelisting, or what some call service binary control, can be incredibly powerful. If PSExec or any other remote admin tool or an unknown piece of malware is not on the approved list of software allowed to run on a particular HMI or server, then it simply won't be allowed to execute, even if the attacker manages to copy it there. We also need to monitor for the appearance of any unauthorized tools or files on our systems, perhaps through file integrity monitoring on critical machines. And just like before, network segmentation plays a huge role. We should design our network segments to limit unnecessary SMB traffic between different zones, and even between hosts within the same zone if they don't need to share files directly. We can block unnecessary SMB ports, like TCP 445 and 139, at our zone boundary firewalls to prevent this kind of traffic from crossing between segments where it's not explicitly needed. For detection and response, we need to be logging things like access to file shares, SMB connection attempts, and especially process execution events on our endpoints. If PSExec.exe suddenly runs on a server where it never normally runs, or if it's launched by a user account that shouldn't be performing remote administration, that should trigger an alert. Network traffic analysis can also help here by monitoring SMB traffic for unusual file transfers. Are large executables being copied between workstations? Is a server suddenly trying to connect to admin shares on a dozen other machines? We should also look at hardening our systems against the theft of credentials that could then be used for this kind of lateral movement via SMB. Things like preventing or limiting the caching of credentials in memory, where tools like Mimikatz could grab them, and of course, restricting who has access to those administrative shares in the first place using strong permissions. So, our blended defense here is use strict network segmentation to control where SMB traffic can even flow. Implement application whitelisting to prevent unauthorized tools like PSExec or malware from being executed, even if they get copied over. Secure your administrative credentials tightly, and harden your systems to prevent those credentials from being easily stolen. And then, monitor your network traffic for suspicious file transfers and your endpoints for suspicious process creations that might indicate an attacker is trying to move tools around. It's about making it hard for them to bring their weapons to the fight and spotting them if they try. How well are you controlling the use of potentially dual-purpose admin tools in your OT environment? One of the first things we need to get much better at is understanding how attackers can use protocol features for nefarious purposes. When we're segmenting our networks, perhaps putting a firewall between two zones, we often think about filtering based on IP addresses and ports. We might say, okay, this PLC in zone A is allowed to talk to that HMI in zone B using Modbus TCP on port 502. And that seems fine on the surface. But we need to consider not just the basic routability of the allowed protocols, but also their encapsulation capabilities. Remember how we talked about tunneling? Many industrial protocols can carry other protocols hidden inside them. So just allowing Modbus TCP might not be enough if an attacker can tunnel a completely different, unexpected protocol through that allowed Modbus TCP connection. Our firewalls and intrusion detection systems need to be smart enough to look deeper into the traffic, to understand these encapsulation methods, and to filter based on the actual protocol being carried, not just the wrapper. Are your segmentation rules truly accounting for these protocol within a protocol scenarios? Secondly, we absolutely must take a detailed inventory and risk assessment of all our perimeters at the lower Purdue levels. Not just the big IT/OT boundary at level 3.5 or 4. I'm talking about the boundaries within level 2, between level 2 and level 1, and even within level 1. We need to identify every connection that crosses into sensitive zones, like those leading to safety instrumented systems, or connections to systems that are managed by external third parties, like those vendor-maintained packaged units we discussed. Document these connections meticulously. What devices are involved? What protocols are they using? What data is flowing? And what are the security properties of that link? Is it encrypted? Is it authenticated? What happens if it fails? This detailed mapping is fundamental. You can't secure what you don't know you have. A key point here, don't assess the risk of a particular link purely based on its intended normal operational capabilities. This is a common trap. We might look at a simple serial link between two controllers and think, oh, that just sends a few analog values back and forth. It's not a high-speed Ethernet link, so it must be low risk. But that's a dangerous assumption. That seemingly innocent serial link still has a protocol stack on each end. It has parsers that interpret the incoming data. And those parsers, even for simple serial protocols, could contain vulnerabilities that a skilled attacker might be able to exploit by sending malformed data. They might not be able to download a huge malware package over it, but maybe they can cause a denial of service or corrupt some critical data values. Every connection, no matter how simple it seems, needs a proper risk assessment based on what could happen, not just what should happen. This leads directly to another crucial defensive measure. If engineering services or special programming functions aren't absolutely required over a particular communication link for normal operations, then restrict their accessibility or disable them entirely. Many controllers and field devices can be programmed or configured over the same network they use for operational data. This is convenient for engineers, but it's also a huge door for attackers. If a PLC only needs to send I/O data to another PLC, it probably doesn't need to accept programming commands from that PLC. So, configure it to reject them. This principle applies even to those nested devices we talked about, the ones that might be reachable through protocol routing from a master PLC. If the master PLC doesn't need to reprogram its slave devices during normal operation, then that capability should be locked down, perhaps requiring a physical key switch or a special engineering connection to enable it. Think about the principle of least privilege, but applied to protocol functions. Only allow what is absolutely necessary for the defined operational task. For those connections where you do need to allow some level of sensitive traffic, perhaps between an engineering workstation and a PLC for legitimate programming, use firewalls with deep packet inspection, DPI capabilities. These are firewalls that don't just look at IP addresses and ports. They can actually understand the industrial protocols themselves. They can look inside the payload of the packets. With this capability, you can write much more granular firewall rules. For example, you could create a rule that allows an engineering workstation to read data from a PLC, like monitoring its status, but blocks any commands that try to write to the PLC's logic or stop its CPU, unless it's within a pre-approved maintenance window or from a highly trusted source. Your rules need to be sophisticated enough to distinguish between normal, benign operational communications and potentially dangerous engineering commands or exploit attempts. Are your firewalls just acting as traffic cops for ports, or are they truly inspecting the content? Now, even with the best firewalls, we need visibility. We need to see what's happening on these critical level 1 networks. So, for your sensitive level 1 boundaries, especially those BPCS to SIS links, or links to critical packaged units, you should develop visibility through dedicated network monitoring and anomaly detection tools. This isn't just for your main Ethernet networks. This includes those serial links we talked about. Serial links can absolutely be monitored. You can use passive tap devices that listen to the serial communication and then report what they see over an out-of-band channel, perhaps to a central security monitoring system. The goal is to be able to see the traffic, analyze it for unusual patterns, unexpected commands, or connections to unauthorized devices. If an attacker starts probing or trying to exploit a vulnerability, you want to have the best possible chance of detecting that anomalous activity before they can achieve their objectives. And speaking of detection, don't forget the devices themselves. Regularly collect and analyze the event logs from your level 1 devices. Your PLCs, your RTUs, even intelligent field devices if they generate logs. I know. These logs can sometimes be cryptic, they might not be in a standard format, and it can be a real challenge to integrate them fully into your main security, information, and event management system, your CIEM. But even if you can't get them into the CIEM in real time, just having these logs collected and stored securely provides invaluable forensic information if an incident does occur. If you suspect a compromise, these logs might hold the only clues about what happened, when it happened, and how the attacker got in or moved around. So, figure out how to get those logs. Even if it's a manual process to start, it's better than having nothing. Beyond just logs, you should also monitor your controllers for anomalous error flags, unusual resource consumption rates, and strange communication patterns. For example, if a PLC suddenly starts reporting a high number of communication errors on a specific port, or if its CPU utilization spikes unexpectedly and stays high, or if its memory usage starts creeping up without a good reason, these could be subtle indicators that something is wrong. It might not be an attacker. It could be a hardware problem or a network issue. But it could also be a sign of an exploitation attempt or the presence of malware consuming resources. These operational parameters can be like an early warning system for your controller's health and security. We also need to think about the code running on our PLCs. We should apply secure coding practices to our PLC logic itself. Yes, PLC programming languages like ladder logic, function block diagrams, or structured text are different from IT programming languages, but many of the same secure coding principles apply. Things like input validation, making sure that data coming from sensors or from other systems is within expected ranges before you use it in your logic. Boundary checking on process values to prevent overflows or underflows that could lead to unsafe conditions. Writing well-structured, modular code that is easier to understand, test, and maintain. Well-designed and robust PLC logic can actually prevent some forms of manipulation, or at least make it much harder for an attacker to cause an unsafe state, even if they manage to change some data values. Think of your PLC logic as another layer of defense. Authentication is another key area. We need to implement authentication mechanisms wherever they are available, even on those traditionally unauthenticated field bus protocols. For many years, most level 1 and level 0 protocols had no concept of authentication. Any device on the network could send a command, and the receiving device would just obey it if the command was formatted correctly. This is changing, albeit slowly. Newer versions of some industrial protocols are starting to incorporate authentication features. Some vendors are offering secure gateways or communication modules that can add a layer of authentication and encryption on top of legacy protocols. Where these capabilities exist, we should be using them. Even if it's not perfect, some authentication is usually better than no authentication. It raises the bar for attackers. Are you actively looking for and enabling these features where possible? And if the worst does happen, we need to be prepared. It's absolutely vital to develop detailed incident response plans that are specifically tailored to OT environments. Your IT incident response plan is a good starting point, but it's not enough for OT. In OT, the priorities are different. Safety is paramount, followed by maintaining operational continuity, if at all possible. Your OT incident response plan needs to include procedures for safely isolating affected systems. And that's a tricky balance, isn't it? How do you isolate a compromised controller or network segment without tripping a critical process or causing an even bigger problem? It requires careful planning, involving both your automation engineers and your security team. You need to know how to contain the threat while keeping the plant running safely, or shutting it down in a controlled manner if necessary. This plan needs to be documented, and just as importantly, it needs to be practiced. Tabletop exercises, simulations, they are invaluable. To make sure all these defenses are working and to find gaps, you must conduct regular security assessments that focus specifically on those level 1 connections and hidden perimeters. Don't just assess the IT-OT boundary and call it a day. You need to go deeper. Penetration tests, vulnerability assessments, architectural reviews, but with a specific focus on these controller-level networks and interconnections. Use people who understand OT systems and OT protocols. They'll know what to look for. They can help you find those hidden tunnels before the attackers do. A very powerful detective control is implementing change detection for your PLC programs and their configurations. If an attacker manages to modify the logic in your PLC, or change a critical set point, or alter its firmware, you want to know about it as soon as possible. There are systems available that can periodically back up the code and configuration from your PLCs and compare it to a known good baseline. If any unauthorized modifications are detected, they should trigger an immediate alert for investigation. This can be a lifesaver for catching subtle manipulations or unauthorized access. And of course, the basics still apply, even at level 1. Apply firmware updates and patches to your field devices and controllers whenever they are available, but always after proper testing in a non-production environment. Many of the protocol stack vulnerabilities or other flaws that attackers exploit for lateral movement do have patches available from the vendors. But we all know the challenges of patching in OT, the "if it ain't broke, don't fix it" mentality, the fear of interrupting operations, the need for extensive testing. These are valid concerns, but we can't let them paralyze us. We need to have a risk-based patching strategy. Understand which vulnerabilities are critical. Test the patches thoroughly, and schedule the updates during planned maintenance windows whenever possible. It's a continuous effort. Finally, and this underpins everything else, you must document all communication pathways and protocols in your entire OT environment, including those at level 1 and even down to level 0 if possible. I can't stress this enough. You simply cannot secure what you don't know exists. Create detailed network diagrams, data flow diagrams, asset inventories. Know what devices you have, what firmware they're running, what they're connected to, what protocols they're using, and what data they're exchanging. This documentation is not a one-time task. It needs to be a living document, updated regularly as your systems change and evolve. It's the foundation of your entire OT security program. How confident are you in your current documentation of these low-level networks? Scenario 3. Attackers using stolen legitimate credentials, like pass the hash or pass the ticket. This is a really insidious one because it can be very hard to detect. Attackers manage to get their hands on legitimate user or administrator credentials. Maybe they got them from a phishing attack that tricked someone into giving up their password. Maybe they used a keylogger on a compromised IT system that an engineer also used to log into OT systems. Or perhaps they dumped password hashes from a compromised HMI or server and then cracked those weak hashes offline to get the actual passwords. Once they have these valid credentials, they can use them to authenticate to other systems in the OT network. And the really tricky part is that to a simple logging system, this might look like normal activity. It's a legitimate account logging in, after all. We know that sophisticated malware like InDestroyer, Crash Override likely used legitimate credentials for at least some of its lateral movement and for its interactions with the ICS protocols themselves, making it blend in. How do we combat the misuse of legitimate credentials? It starts, once again, with really strong access control policies and practices. This means strong, unique passwords for every single account. No shared accounts, no default passwords left unchanged. And again, multi-factor authentication, MFA, is your friend here, especially for any privileged accounts or for any remote access into the OT network. If an attacker has the password, but not the MFA token, they're still locked out. We also need good account management practices. Regularly review all user accounts, disable any that are dormant or no longer needed, and enforce policies for regular password changes and password complexity. And of course, always apply the principle of least privilege. Just because an account is legitimate doesn't mean it should have access to everything. Then, we need to think about use control. Even if someone authenticates with valid credentials, are they actually authorized to access the specific system or data they're trying to reach? Authorization controls should ensure that users are only accessing what they are specifically permitted to access based on their role and responsibilities. For detection and response when legitimate credentials are abused, this is where things get more advanced. We need to log all authentication attempts across all our systems, successful logins, failed logins, everything. And then we need to monitor those logs for anomalous login patterns. For example, is a user account suddenly logging in from a workstation it has never used before? Is an account logging in at 3 a.m. when that user only ever works day shifts? Are there multiple failed login attempts for an account from one location, quickly followed by a successful login for that same account from a completely different, unexpected location? This could be a sign of impossible travel if the locations are geographically distant. Are we seeing concurrent logins from different locations using the same account credentials? This is where user behavior analysis, UBA, or user and entity behavior analytics, UEBA tools can be incredibly valuable. These tools learn what normal behavior looks like for each user and for each system, and then they can flag deviations from that baseline, even if valid credentials are being used. For instance, if an engineer's account suddenly starts trying to access a part of the control system it has never touched before, or starts running unusual commands, a UBA system might pick that up. We also need to harden our endpoints to prevent those credentials from being stolen in the first place. This means things like disabling the caching of credentials in memory, like in LSAS on Windows, wherever feasible, or using technologies like Microsoft's Credential Guard if you're on a compatible Windows version. We should also monitor for any plain text credentials being transmitted across the network or any insecure handling of credentials. And of course, having strong password policies that enforce complexity and regular changes helps make them harder to guess or crack. So, the blended strategy here is MFA is a huge deterrent against the use of stolen credentials. Enforce strong password policies and the principle of least privilege rigorously. Harden your endpoints to make it much harder for attackers to steal credentials. And then, critically, deploy user behavior analysis and advanced authentication log analysis to try and detect those anomalous activities that might indicate legitimate credentials are being misused by an attacker. Network segmentation also helps here, because even if an attacker gets a set of credentials, segmentation can limit how far they can go with them. It's a tough challenge, but not an insurmountable one. Are you just checking if a login is valid, or are you also looking at whether that login behavior is normal? Let's consider another one that's a variation on remote services. Scenario 4. Attackers abusing Windows Remote Management, WinRM. Windows Remote Management, or WinRM, is a legitimate feature built into modern Windows operating systems. It's designed to allow administrators to remotely manage servers and workstations, run scripts, execute commands, and so on. It's quite powerful. And, of course, attackers have realized this too. They can leverage WinRM to move laterally across any Windows-based systems they find in the OT environment. Think HMIs, engineering workstations, data historians, SCADA servers. This usually requires them to have already obtained administrative credentials, perhaps through one of the methods we just discussed. But once they have those credentials, WinRM can be a very effective and often less monitored way for them to control machines remotely. What's our defense against WinRM abuse? Well, many of the same principles apply. Strong access control is essential. Who has the admin rights that would allow them to use WinRM on other machines? Those accounts need to be very tightly controlled and protected with strong passwords and MFA. And the principle of least privilege is vital. Then, network segmentation and restricted data flow come into play again. We need to segment our networks to limit which systems can even communicate with each other using the WinRM protocol, which typically uses HTTP or HTTPS over ports 5985 or 5986. Can we use host-based firewalls on our HMIs and servers to restrict WinRM access to only come from specific authorized management servers, rather than allowing it from anywhere on the network? That would significantly reduce its potential for abuse. For detection and response, we need to enable and collect the operational logs for WinRM. Windows does have specific event logs for WinRM activity, like the Microsoft Windows WinRM operational event log. These logs can tell us if WinRM is being used, from where, and sometimes what commands are being run. We need to monitor these logs for any suspicious WinRM activity. Network traffic analysis can also help by watching those WinRM ports for unusual connections or for patterns that might indicate command execution or data transfer. We should also be monitoring our endpoints for processes that are being spawned remotely via WinRM. If a strange script suddenly runs on a server and the parent process is related to WinRM, that's worth investigating. And of course, logging the actual command lines executed via WinRM sessions gives us even more visibility. Some host-based intrusion prevention systems might also be configurable to detect or even block suspicious WinRM usage patterns. And importantly, we need to harden the WinRM service itself. If it's not needed on a particular system, it should be disabled entirely. If it is needed for legitimate remote administration, then it needs to be configured as securely as possible. For example, we should enforce the use of HTTPS, WinRM over SSL on port 5986, to encrypt the traffic, rather than using unencrypted HTTP. We should also restrict which network interfaces WinRM listens on and configure trusted hosts if possible. So, the blended defense strategy for WinRM abuse is, if you absolutely need WinRM, harden its configuration, use HTTPS, restrict listeners. Apply very strong access controls to any accounts that are permitted to use WinRM. Segment your network to limit the exposure of the WinRM service and control who can connect to it. And then enable comprehensive logging of all WinRM activity and use network and endpoint monitoring to look for any suspicious commands or process creations coming through WinRM. It's about making a legitimate tool much harder for an attacker to turn against you. These are just a few examples of how attackers can move laterally using IT-like techniques that can also affect our OT environments, especially where Windows systems are prevalent. But what about the unique aspects of OT? Scenario 5. Attackers exploiting weaknesses in native ICS protocols for lateral movement. This is where things get really specific to OT. Imagine malware, perhaps something sophisticated like some variants of Indestroyer were, or maybe a new hypothetical threat. This malware could be designed to exploit known vulnerabilities or even just inherent weaknesses, like a complete lack of authentication in the common industrial protocols that our PLCs and field devices use to talk to each other. I'm talking about protocols like Modbus, DNP3, Siemens S7com, BACnet, and many others. If these protocols are not secured, an attacker who has a foothold on one device on an OT network segment, say a compromised HMI, might be able to send malicious commands directly to PLCs or other controllers on that same segment. They could potentially reconfigure a device, stop it, start it, or change its set points. And here's where the lateral movement part comes in at this low level. They might reconfigure one PLC in such a way that it then adversely affects another PLC or device that it communicates with, or they might use one compromised controller as a sort of stepping stone, a proxy, to then send commands to other PLCs or intelligent field devices that weren't directly reachable from their initial point of compromise. For instance, if a PLC is connected to both a main control network and a separate, dedicated I/O network for its sensors and actuators, an attacker who compromises that PLC via the control network might then be able to use the PLC itself to send malicious commands out onto that I/O network to manipulate other devices. This is a very direct way to move through the control system fabric. So, how do we defend against this kind of abuse of our core industrial protocols? Well, first, wherever your industrial protocols actually support authentication or secure modes of operation, you absolutely need to use them. Newer versions of some protocols, like DNP3, Secure DNP3, or Siemens S7, S7com Plus with security features, do offer these capabilities. Enabling them can be a significant step in preventing unauthorized devices or software from injecting commands. It's not always easy to implement, especially in older systems, but it's something we should always be striving for. Then, we have to think about protecting the integrity of the communications themselves. If your protocols don't have strong, built-in security, and many widely used legacy protocols simply don't, then you need to look at compensating controls. This could mean wrapping that insecure protocol traffic within a secure tunnel, perhaps using IPsec VPNs between critical devices, or using TLS to encrypt the sessions if the devices support it. The goal is to make it much harder for an attacker to sniff the commands, modify them in transit, or inject their own malicious messages. And of course, securing physical access to the network ports on these devices is also crucial to prevent someone from just plugging in and starting to talk to your PLCs. But perhaps the most powerful defense against this kind of lateral movement is rigorous network segmentation, specifically designed with your ICS protocol flows in mind. You need to know with absolute certainty which devices need to communicate with which other devices, using which specific industrial protocols, and even which particular functions or commands within those protocols are legitimate for normal operation. Once you have that map, you need to implement strict firewall rules, ideally using firewalls that are ICS aware, meaning they can actually understand and parse those industrial protocols, not just look at IP addresses and port numbers. For example, you could write a rule that says HMI A is allowed to send Modbus read holding registers commands to PLC B on these specific registers, but it is not allowed to send any Modbus write commands, and no other device is allowed to send any Modbus commands to PLC B at all. This kind of granular, allow only what's absolutely necessary policy enforced at your internal network segment boundaries can dramatically limit an attacker's ability to send malicious commands, even if they manage to compromise a host on that segment. And for detection and response, this is where network security monitoring, NSM tools with deep packet inspection, DPI, capabilities tailored for ICS protocols become so incredibly valuable. These tools can passively listen to your OT network traffic, decode the actual Modbus, DNP3, S7, or other commands being sent, and then compare that traffic against your defined policies or known malicious signatures. They can alert you to things like someone attempting to send a stop PLC or download new program command from an unauthorized source or at an unusual time, a device suddenly sending a flood of malformed or unexpected DNP3 messages, which could indicate an exploit attempt or a device malfunction, an HMI trying to write to a memory register in a PLC that it should, according to your policy, only ever be reading from. These tools can give you very specific, actionable alerts about the misuse or abuse of your critical control protocols. Another interesting technique for detection is the use of ICS honeypots. These are decoy systems that you place on your network that look and behave like real PLCs or other ICS devices. If an attacker is probing your network, looking for vulnerable devices, and they happen to stumble upon and interact with one of your honeypots, it gives you a very early warning that someone is snooping around where they shouldn't be. Finally, ensure your devices are configured for proper protocol conformance. This means they should be set up to reject any messages that are badly formed or don't comply with the protocol standard, as these could be part of an attack attempt. So, the blended defense strategy here is robust network segmentation based on a deep understanding of your legitimate ICS protocol flows is your absolute cornerstone. You then back this up with continuous network traffic analysis using ICS-aware DPI tools to watch for any unauthorized or malicious commands trying to sneak through those allowed paths. Wherever possible, you should be using secure or authenticated versions of your ICS protocols, or implementing compensating controls like VPNs or TLS wrappers to protect the data while it's in transit. And consider using ICS honeypots as an additional layer for early detection. This is all about meticulously locking down and monitoring how your core control system components are allowed to communicate with each other. How confident are you right now that you know exactly what your PLCs are saying to each other and who else might be trying to talk to them? It's a critical question. Now let's bring it back to those specific countermeasures we discussed earlier for deep lateral movement, especially at that critical level 1. These are really important, so let's take a moment to review them as a kind of checklist for action. Let's review 15 critical, not negotiable countermeasures that can really help protect against deep lateral movement in your OT networks. First, when you're segmenting your systems, remember to consider not just the routability of the protocols you're allowing, but also their encapsulation or tunneling capabilities. Don't let attackers sneak things through by hiding one protocol inside another. Your filters need to be smarter than that. Second, really take stock of all those perimeters down at the lower Purdue levels, especially any that cross into sensitive zones like your safety systems or those connections to systems managed by external parties. Document them, understand their security properties, know your internal boundaries. Third, a crucial mindset shift. Do not assess the risk of a particular link purely based on its normal, intended operational capabilities. That innocent-looking serial link might still have vulnerable parsers that could be exploited. Think about what could go wrong, not just what it usually does. Fourth, if specific engineering services or programming functions aren't absolutely required over a particular link for day-to-day operations, then restrict their accessibility or disable them entirely. This applies even to those nested devices that might be reachable through protocol routing. If it doesn't need to be open, lock it down. Fifth, for those sensitive level 1 boundaries where you do need to allow some critical traffic, use firewalls that have deep packet inspection, DPI capabilities that understand your industrial protocols. Your rules need to be granular enough to distinguish between normal operations and potentially dangerous engineering commands or exploits. Sixth, for these sensitive level 1 boundaries, especially between different security zones like BPCS and SIS, actively develop visibility through dedicated network monitoring and anomaly detection tools. And yes, this includes those serial links. They can and should be monitored too, perhaps with taps reporting via out-of-band channels. Seventh, make it a practice to regularly collect and analyze the event logs from your level 1 devices, your PLCs, RTUs, and intelligent field devices. Even if you can't get them into your main CM easily, having these logs for forensics is invaluable if an incident occurs. Eighth, monitor your controllers for anomalous error flags, unusual resource consumption rates, like CPU or memory, and strange communication patterns. Sudden changes in these operational parameters might be an early indicator of an exploitation attempt or malware activity. Ninth, think about security even in your PLC code. Apply secure coding practices to your PLC logic itself, including things like input validation for sensor data and boundary checking on critical process values. Well-designed logic can actually prevent some forms of manipulation. 10th, implement authentication mechanisms wherever they are available, even on those traditionally unauthenticated field bus protocols. Many legacy protocols lack strong authentication, but newer versions or specialized secure gateways may offer these capabilities, so seek them out and use them. 11th, this is non-negotiable. Develop detailed incident response plans that are specifically tailored to your OT environments. These plans must include procedures for safely isolating affected systems while trying to maintain critical operations or for performing a controlled shutdown, and practice these plans. 12th, your security assessment program needs to go deep. Conduct regular security assessments that focus specifically on these level 1 connections and those hidden internal perimeters, not just on the traditional IT-OT boundary. Get experts who understand OT to help you. 13th, a powerful detective tool. Implement change detection for your PLC programs and their critical configurations. Any unauthorized modifications to PLC logic, firmware, or key set points should trigger an immediate alert for investigation. 14th, patching is still important. Apply firmware updates and security patches to your field devices and controllers when they are available from your vendors, but always after thorough testing in a safe, non-production environment. Have a risk-based patching strategy. And finally, number 15, underpinning all of this. Meticulously document all communication pathways and all protocols used in your entire OT environment, including those at level 1 and even below if you can. You cannot effectively secure what you do not thoroughly understand and have documented. This is a living document, a constant companion to your security efforts. These 15 points provide a really solid framework for thinking about how to defend against those deep lateral movement threats that target the very heart of our control systems. So, let's take a moment to summarize what we've covered today, because it's been a lot of information. We've seen that deep lateral movement in our OT networks represents a very sophisticated and dangerous attack vector. It focuses on attackers traversing boundaries right down at the controller level, at Purdue level 1. These techniques can allow them to do very damaging things, like crossing critical security perimeters between our basic process control systems and our vital safety instrumented systems, or they might use these techniques to gain extremely granular control over specific field devices, allowing for very targeted and potentially destructive attacks. We talked about the primary methods attackers use to achieve this. Things like exploiting the native routing and tunneling capabilities of many industrial protocols, performing in-band code downloads to controllers or field devices if that function isn't properly secured, using direct memory manipulation to subtly alter how a controller behaves without changing its main program, and of course, exploiting vulnerabilities in the protocol stacks of these embedded devices. We also saw how real-world malware, like the infamous Triton that targeted safety systems, and the more recent in-controller Pipe Dream toolkit, have demonstrated these very capabilities out in the wild. This isn't just theoretical, it's happening. And most importantly, we've discussed that defending against these advanced threats requires a really comprehensive approach. It goes far beyond just protecting that traditional IT-OT boundary. It means we have to truly understand all those complex interconnections that exist down at level 1 of our control systems. We need to be actively monitoring these connections for any signs of trouble. We must restrict any unnecessary functionality on these devices and links. And we need to implement defense in-depth strategies throughout our entire control system architecture, not just at the edges. A key takeaway I want you to remember is this. Security perimeters exist at all levels of the Purdue model, not just at that main IT-OT boundary we so often focus on. Those level 1 devices, the PLCs, the couplers, the gateways that connect multiple networks or bridge different segments should be treated with the exact same security rigor, the same level of scrutiny as any other perimeter device in your architecture, like your main corporate firewall. Truly understanding what connects to what, and just as importantly, how it connects and what it's allowed to do, is absolutely fundamental to building effective OT security in today's threat landscape. Thank you all so much for your attention and for joining me in this deep dive today. I genuinely hope you've gained some valuable insights into this critical area of industrial cybersecurity. It's a complex topic, but understanding these advanced techniques that attackers are using is always the very first step toward building more resilient, more robust defenses for our vital critical infrastructure systems. So, stay vigilant out there, keep learning, keep questioning your assumptions, and always remember that security is not a destination you arrive at. It's a continuous journey, an ongoing process of improvement and adaptation. Keep up the great work you all do in protecting these essential systems.